Our next step in our journey through calculus is we're going to be talking about areas. Now, it's kind of a jump from what we've done before, since we've always been talking about slopes. This is really the second half of calculus. It's differential calculus, talking about the derivative slope, and we're getting into what we're going to call integral calculus, which is all about integration. And the idea behind integration is it's going to mean areas. I'm going to start off thinking about kind of things that make sense. You travel at 50 miles per hour for 2 hours. How far do we travel? Well, we know that distance is rate times time, and so our total distance, we're going 50 miles per hour for 2 hours. Okay, obviously that's going to be 100 miles. All right, makes sense. Graphically, if you look at this, we're going at 50 miles per hour. It's this steady constant. And if we look at time, 0 to 2 hours, that is kind of all of this. We're taking that velocity over that time. We actually have here an area of 100, in this case, miles, since we're talking about time in hours to miles per hour. Let's say we travel at a rate of 25 miles per hour for 1 hour, and then 50 miles per hour for the second hour. What's our total distance? Now, graphically, we're going over the same idea, 2 hours, so that's our time in hours. Now we're going 25 miles per hour for 1 hour, and then we're going at 50 miles per hour for a second hour. So for that first hour, we've traveled a total of 25 miles. That second hour, we've traveled a total of 50 miles, and we've got a total of 75 miles traveled. So that's miles per hour. And we can think about that as if we were to graph the velocity, our miles per hour versus time, then miles per hour multiplied by time, our rate times time, gets us our total distance. Well, that's an area. So if we're taking the area traveled in one, adding that to the next. But what if it's not constant like that? What if we travel at a rate that increases over time? Now, I'm saying our velocity is given by 25t. So that means after 1 hour, we are traveling at 25 miles per hour. At 2 hours, we're now traveling at 50 miles per hour. I'm just going to keep the same time, hours, miles per hour. Well, we want to really find the area that's been added up. And it kind of intuitively, we still have that distance equals rate times time. That's the worst T ever. Distance equals rate times time. But our rate is constantly changing. From before, well, I can see that the velocity compared to the time, I'm going to be multiplying that velocity times the time, getting that area underneath those curves. It stands that our total distance is, again, that area underneath that curve. So how do we find that? You go, oh, well, that's a triangle. I know the area under a triangle is 1/2 base times height. In this case, we've got 1/2 our base is a total of 2 hours multiplied by our height. Our height is changing, but our height at the end is 50. So our area of that triangle is going to be 50, but interpreting it in terms of velocity, time, distance, that's going to be a total of 50 miles traveled. But what happens if it is not a nice geometric figure? What if it's not a rectangle? What if it's not a triangle? Let's say we travel at a rate of t squared. How far do we travel over that time? So now, just going from 1 to 2, we've got this curve. That's 1. At 2, that's at 4. If that's our velocity, so miles per hour, I know 1 to 4 miles per hour is not that fast, versus hours, well, the same kind of idea applies. We want that area underneath that curve, but it's not a nice geometric shape. So how do we do it? We know it's got to be greater than 0 just by looking at it. We know it has to be less than 8. And I know it's got to be less than 8 because I can look at, ooh, there's one big rectangle there. So it's got to be less than 8, which is 2 by 4. It's got to be greater than 0, which is no rectangle at all. So how do we figure that out? Well, we could make a small rectangle from 0 to 1, and then a larger rectangle there. Well, that's got an area of 1, and that's got an area of 4, so kind of geometrically we know that it's less than 5. That's using 2 rectangles instead of 1 big rectangle. What happens if we use some smaller rectangles? If I break this apart, well, there we can find that area, that rectangle, that area, that rectangle. Kind of finer and finer details. So how far can we go? And that's the issue that we're going to be looking at. How do we take that? We can always take smaller and smaller partitions. We can use 4 rectangles to approximate it, to make it look like the curve. 8 rectangles, 16 rectangles. Smaller and smaller rectangles, we get a better and better area. That's where our calculus comes in. Smaller and smaller rectangles. Get this idea more and more. As the number of rectangles increases, as that number of rectangles increases towards infinity, we would have a really accurate representation of that area. So there's our limit. All of those rectangles, really, really thin, would get us an accurate representation of the area. Connecting back to limits. Happy days. So let's take a look. We've got this curve, the area under the curve, from some A to B. How can we determine that? Now, the last one, I was looking at parabola, but it could be any curve. We know area of a rectangle. We can do that. Anything that's triangular, we can find the area. Really, any polygon, anything with straight sides, we can always partition into separate rectangles or triangles and easily find the area by that curved figure. So this is what I just looked at from y equals x squared between 0 and 1. How do we approach that? Using this idea, we can take it and separate it into smaller components and approximate it. Now, on the first one, I'm splitting it up into 4 different intervals. Now, I can approximate this with some rectangles. Now, here, the first setup, all of my rectangles, I've been splitting this up into 4 intervals. I'm taking a rectangle starting at the right side of that interval. The one on the left, the right, should have made that better, making really rectangles that start on the left side of each of these intervals. And so what we can see is that, all right, less than the area of this, greater than the area of this, something in between. Now, historically, Archimedes had this idea of 2,000 years before Newton, approximating with polygons, circumscribing and inscribed in a circle, and he was approximating pi. 1,000 years ahead of his time, actually kind of using calculus. So we're going to break this apart and use finer and finer partitions. We can keep on separating this apart, using left endpoints, using right endpoints, smaller and smaller rectangles, getting a better and better lower estimate, and a better and better higher estimate, an upper estimate. So it's got to be something in between the two of those. Now here, I've got a table with an increasing number of strips. Now this is for that curve, y equals x squared, from x equals 0 to x equals 1. If we take a larger and larger number of rectangular partitions, what happens as that number approaches infinity? So we look at the table that's already been calculated for us. So we've got 10 rectangles, 20 rectangles, 30 rectangles, 50. As those are getting larger and larger, well, it's going to be increasing, or in this case decreasing, but is it closing in on some middle number? If we have 1,000,000 rectangles, it kind of looks like it's approaching 1/3. So how do we verify that? How can we actually get something that tells us that? So I'm going to take the limit as our number of rectangles is approaching infinity. And I'm using this r sub n. That's saying that I have rectangles starting on the right side of our interval. So this is a right-sided rectangle because our interval starts there, ends at 1, and the rectangle, the height, since it's based on height, the height is on the right side. This next rectangle from the right, that interval, a rectangle starting on the right side. This rectangle, the height of that rectangle is on the right side, compared to these rectangles where my rectangular approximations are starting from the left. Now, we notice that if we've got n many rectangles, the width of each rectangle, since we're going from 0 to 1, is 1 over n. So the width of each rectangle is 1 over n. Now, where that rectangle comes into play is this 1 over n squared, or 2 over n squared would be the second rectangle, 3 over n squared would be the third rectangle, etc. I could factor all of that out and turn this into this expression, where every single time we've got this 1 over n squared, over n squared, over n squared. I can factor that out as 1 over n squared, giving us 1 over n cubed. That then represents, or we can rewrite that as the sum of square numbers. And maybe we recall from past experience in pre-calculus that with finite differences could be found with a regression. There is a formula for the sum of n many perfect square numbers. And that is n multiplied by n plus 1 multiplied by 2n plus 1 over 6. So as we approach an infinite number of rectangles, we have this expression that gives us really the area, the total sum of all those rectangles. Applying a limiting factor, You can follow that, looking at this, multiplying it out, looking for common values, and then as n approaches infinity, well, that goes to 0, that goes to 0. We've got 1/6 times 1 times 2 gets us an algebraic 1/3. So looking at the table of the limits, it approaches 1/3. Now, analytically, algebraically, applying our limits, we can also see that using this sum, we can solve it and evaluate the limit, getting 1/3. It's a lot of work to get there. But here's the concept. As that n value both increases, both the left rectangles and the right rectangles become better and better approximations for the area. So that's how we're going to define area. Area is this limit of the sums of those approximating rectangles. As the number of rectangles becomes greater and greater and greater, the sum, that limit, will approach the exact area. So the area under the curve is the limit of the sum of those rectangles as the number of rectangles approaches infinity. Given any curve, any width, so I've got some arbitrary curve, we're going from A to B. We're going to split this into n many rectangles. So the width of the interval from A to B is going to be the difference between the two endpoints. So it's that value, subtract that value. If we're going from 3 to 5, that width would be 5 minus 3 is 2. Since we have n many rectangles, the width of each rectangle I'm going to represent as delta x, Greek letter delta for change, or that's going to be the width of x, is the difference divided by the number of rectangles. We then have n many subintervals, starting from the left, a, plus delta x to get us to the end of that first interval, then the next interval from x sub 1 to x sub 2, then from x sub 2 to x sub 3, all the way down to the end from x sub n minus 1 to the end point x sub n, in this case b. Now, evaluating that, since each one we're going to be adding the width of each rectangle, it's the starting point plus 1 width of the rectangle. The next one would be the starting point plus 2 times the width of the rectangle, and so on. We can combine all this, the sum of all those rectangles, using that right rectangular approximation, the right rectangles, is going to be the height times the width, plus the next height, there's that, times the width, plus the next height times the width, so on until we get to the final height times the width of that rectangle. So we can represent the sum, or the area is the sum of all those rectangles. Now in this case, I'm using right rectangles. Perhaps next time we'll use left rectangles, or a different point. What we want then is what happens as the number of rectangles keeps on increasing. So here you can see examples where we've got 2 rectangles, 4 rectangles, 8 rectangles, 12 rectangles. It becomes a better and better approximation to the value of the curve. Here I would say that this is an underrepresentation because we've got all this area that's not covered. Now there's less and less area not covered and less overestimate as we get finer and finer estimates. So another way of thinking about this is that the area of this region that lies under the graph of some continuous function, it's the limit of the sum of those approximating rectangles. And I can represent that using our limit notation. The limit as the number of rectangles n approaches infinity for our right side is, remember, x sub 1 is the right side of that endpoint times the width. That's the base times the height of the rectangle, plus the base times the height. Actually, I put that backwards. That's the height of the rectangle times the base, plus the height of that rectangle times the base, plus so forth. It's the sum of n many rectangles as we're going approaching infinity. We could represent the same thing from the left. I'm using x sub 0, x1, all the way to xn minus 1 because we're taking rectangles that start on the left side. Starting 0 would go over, starting at x sub 0, then x sub 1, then x sub 2, until we get to x sub 3. So in this case, we shift over by 1. It's really the same thing, it's just we're taking rectangles starting on the left side. We could also say this is for any point inside of some interval. So if we have some interval, delta x, remember, b minus a over n, the endpoints divided by n is the width of each rectangle. It could be at any point inside that interval. Really, we could choose what's an appropriate value, what gives us the least amount of wasted space or overestimate. I'm going to represent that as x sub I with a star. So the area does not matter on rectangles that start on the left or the right. It can start anywhere over an interval. And so it's always the height times the base. Height times the base as the number of rectangles approaches infinity. Now we can use a common notation is this sigma notation. The Greek letter S is this sigma. Perhaps you've seen this in statistics before. This means sum. So this is the short way of representing a repeat sum. Perhaps you saw this last year in pre-calculus when you're talking about series. A series is a sum of values. So the sum of n many rectangles can be rewritten with this expression. So I would read this as sigma, or the sum from the starting value I is 1 to n is, or the sum of the heights multiplied by the width of each rectangle. And I'm going to use this subscript x of I to mean the ith rectangle, the first rectangle, the second rectangle, the third rectangle, etc., all the way up, stopping at the nth rectangle. So this notation is the shorthand that represents all of this entire sum. Combining this with our limit, this idea that the area is the limit as n approaches infinity of either our right rectangles, our left rectangles, or any point in any rectangles formed with any point inside the interval, we can shorten this using our summation, our sigma notation, as such. This, the last one, just generalizes the previous two. Using this to represent right rectangles, that represents left rectangles, and x of I is any point on our interval. So let's try this out. I'm going to use this function. We're taking f of x equals e to the negative x between 0 and 2. I'm going to rewrite or write a limit expression that gives us the area underneath that curve. Now, previously, just copying over, we have area is the limit as n approaches infinity, of taking it generally from I equals 1 to n of f of x of I times delta x. Is like the worst sigma ever. If you look at my calc notebooks from when I was in college, I spent hours practicing how to make a sigma. That one's not too bad. We have that f of x is this function, e to the negative x. Delta x, remember, it is b minus a over n. So in this case, since we are going between 0 and 2, our delta x is going to be 2 minus 0 over n is 2 over n. So our limit would be written as the limit as n approaches infinity of a sigma from I equals 1 to n of our function e to the negative x multiplied by, it's going to be e to the negative x sub I, because the I represents the endpoint of our rectangle, multiplied by 2 over n. And so neatening this up, using some properties of summations, since that 2 is a constant, we can factor that out. This is the limit as n approaches infinity of 2 multiplied by the sum from I equals 1 to n of e to the negative xi over n. Done. I've written the area as a limit. Now let's actually try this. I'm going to estimate the area using 4 subintervals and sample points at the left endpoints, the right endpoints, and at midpoints. So what's drawn in here is we've got 4 intervals. We're going from 0 to 1/2, from 1/2 to 1, from 1 to 1.5 to 3/2, and from 3/2 to 2. So that gives us 4 different subintervals. I'm going to use 4 rectangles. What's drawn in there are rectangles approximating our area the middle of each interval. So the midpoint there would be 1/4, the midpoint would be 3/4, and it's 3, 3/4, the midpoint there would be 5/4, the midpoint there would be 7/4. So we're going to do this 4 subintervals using left endpoints, right endpoints, and those midpoints. So I'm going to say R sub 4 for right side rectangles each rectangle, so delta x, take that for right rectangles, is going to be f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x plus f of x sub 4 times delta x. But 4 rectangles. Now, looking at our endpoints on the right side, we're going to have a rectangle that starts at the right side of the first endpoint, it's 1/2. The right side of the second rectangle is 1. The right side of the third interval is 3/2. The right side of the fourth is 2. Our delta x is going to be 2 minus 0 divided by 4, and we can see that above. The width of each rectangle is 1/2. I forgot my x. So, for right rectangles, it's going to be f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2 plus f of 2 times 1/2. We can substitute that into the calculator and find some values for that. If we're finding the L sub 4, so I'm going to say 4 left rectangles. Looking at our intervals, our 4 intervals are going to start at 0, would be the first rectangle. Wait for that. So there would be our first left rectangle, our second rectangle, our third rectangle, and our fourth left rectangle. Our first is going to start at 0, second at 1/2, third at 1, fourth at 3/2. So it's going to be f of 0 multiplied by 1/2 plus f of 1/2 multiplied by 1/2 plus f of 1 multiplied by 1/2 plus f of 3/2 multiplied by 1/2. And again, we can substitute that into the calculator. I'm not going to evaluate that in a numerical value because I'm not going to take the time to plug e to the negative x into the calculator right now. Lastly, we can take rectangles starting in the middle. So I'm going to use an M starting for middle rectangles. We've got 4 intervals. Again, our width, delta x, is 1/2. We're going to have 4 rectangles. Now here, I'm going to reference the diagram. We've got rectangles starting, or built, with the height defined in the middle of each interval. So 1/4, 3/4, 5/4, and 7/4. So for middle rectangles, we get f of 1/4 times 1/2 plus f of 3/4 times 1/2 plus f of 5/4 times 1/2 plus f of 7/4 times 1/2. And we could again evaluate that in the calculator. It would be more accurate if we had more than 4 intervals. If we had 10 intervals, 20 intervals, but you can see that actually computing that out might be a bit cumbersome. That's what we're going to play around with. See you soon.